All right, we can get started. So, hi everyone. I'm Kenneth Huang from Penn State University. Thanks for having me here. I was super excited to talk about visual storytelling, and this is a pre-recording video I prepared for the student as a practice talk. So, thanks again for having me. I'm Kenneth Huang, and today we are going to talk about a interesting vision to language task, which we call visual storytelling. So before we get started, a little bit about me. I am Kenneth Huang. I am a fourth year assistant professor at Penn State, and my research focus on the intersection of natural language processing and human-computer interaction. And I try hard to balance our publication in half should be in the NLP venue and the other half is in the HCI venue. And so I care deeply about how people use NLP technology, and I also try to create new NLP technology for people to use. So today we are going to talk about three topics. First, we are going to talk about the birth of visual storytelling tasks. In particular, I kind of want to focus on the thinking behind this task. Why do we think this is a good idea? And what context did we respond to when we introduce the task? And we will also talk about some recent development of the visual storytelling technology, in particular, how to generate short stories based on short sequence of photos. And finally, we'll quickly go through some applications I believe is legit, and there are a lot of potentials. So we will conclude the talk by talking about some future possibilities, okay? So let's start with the birth of visual storytelling. Basically, why did we introduce this kind of weird task, and how do we design the task, and what's the thinking behind this? And this part of talk will mostly focus on our very initial paper that introduced this task and data set to the community. So the context of this task, this visual storytelling task, is the thing happened between 2013 to 2016, which we call vision and language explosion. And that means between this period of time, between 13 to 16, there are several very, very important vision to language or vision and language data set and task was introduced to the AI, NLP, and computer vision community. Probably one of the most famous is the VQA, visual question answering, and the MS COCO caption data set released in 2015. And the visual genome from Stanford was released in 2016. And we also have something like Flickr 30K entities. So there are many vision to language work, data set, and model was released during that period of time. So, but back then, we look at this data, and one thing we kind of notice is that many of the language that people try to annotate or collect on top of the image focus a lot on direct and literal descriptions, right? If you look at the left-hand side, a group of people that are sitting next to each other, which is a very descriptive description of the image, it is definitely correct. It's very descriptive. And the middle one, the descriptive caption can be adult male wearing sunglasses lying down on black pavement, right? And these are probably still very popular nowadays. However, if you think from the NLP or language perspective, when we try to narrate these scenes or these images to your friends, the language you use is more like, for example, left-hand side, this picture, you will probably say having a good time, bonding and talking with friends, for example. And the middle one, probably you will say John got exhausted by the heat, right? And the bracket M means the placeholder for male names. So you will see there's a gap between the descriptive caption we have and the evaluative or more figurative language that people kind of use to describe the situation. So we kind of want to say, okay, can we collect some language that is closer to the day-to-day language? That's the kind of the higher level motivation. So if you narrow it down, right, the differences between sitting in the room and the bonding, a group of people bonding with each other is there's a gap there. You kind of want to capture still want to capture the visual grounded situation in the story, but you kind of also want to facilitate more evaluative or figurative language to include more social relations and emotions that we have in our human society. So that's the higher level motivation of this task. And we back then, we actually, before the actual paper, we actually publishing other survey paper. We look into all the vision to language data set, or at least all the famous ones that we can get access to. And we do a set of a bunch of analysis on this data set. And one thing we kind of found is that when we analyze the ratio between concrete versus abstract terms in the language in those data set, they are probably at the same level of the Brown data set as a benchmark. Brown data set is a classic NLP data set that covers, is co-balanced because it sample data from different genres. It has news, it has book, so it covers a lot of different genres. So on average, the ratio of abstract terms is around 15%. And in the paper, we have more details, but the concept of abstract terms versus concrete terms is that abstract terms covers more abstract idea or concept like love or think. And concrete terms means the language refer to the objects or concrete events. And if you calculate the ratio, you'll find that some data set is much lower, and many data sets only similar at a similar level of the Brown data set. However, we kind of want to push a little bit, right? We want to collect the data set that has more abstract terms. Let's say probably more than 15% of abstract terms. So we kind of encourage this kind of language in the data. So, okay, so that's all the context. And what's the design constraint we were given? So basically, we kind of know we are going to collect the vision and language data. And we have a very rough idea. We are going to collect n some images, and we want to map it to one story, right? And we kind of want to encode real world human activities in these stories. We don't really want to focus on like imaginary story or on realistic story. We kind of want to focus on real world events. And we also kind of want to make sure the images we collected, it's not a set, it should be a sequence that has some order. So the story actually can follow the order of the images. And lastly, we also kind of know, based on our experience in collecting data for machine translation, we know that it will be very useful if for every instance, for every image sequence, we can collect multiple reference. So these are all the constraints. And after a few iterations, I remember we spent probably more than a month to discuss what is the best way to do it. At the end of the discussion, we kind of conclude, okay, let's do it this way. This is what our decision. So let's say, okay, let's find a photo album on Flickr. And we need to figure out a way to focus on those albums that basically capture a human activity, a event in real world, right? In this particular example, it's a wedding. And we show the entire photo set, photo album to a crowd worker. And we ask the worker to pick 5 photos. And it need to be kind of representative photos so that people know it's a wedding, and it's better to capture some important moment of this event, such as etc. So we have a set of instruction teach people how to do that. So you need to select 5 photos to form a photo sequence. By default, the order is the photo taken time. But if you think, if the people think, oh, there are actually better order that can help me tell a better story, they can alternate the order. But by default, everything is sorted by photo taken time. And after you form the photo sequence, you will need to write a story, short story that describe this photo sequence. Okay, that's at a very high level, that's the data collection process we went after. So let's talk a little bit more about the data source. So back then, we decided to use Flickr album, and we know people can, on Flickr, people can put a set of photos together and organize them in the same Flickr album. And so we use some trick. We focus on those photo albums that has 10 to 50 photos. And all the photo inside that photo album need to be taken within a 48-hour time window. So it's more likely to be an event, right? And also, we use some data-driven method, because Flickr's photo, you can add tag, you can add a description, and you can actually use those information to figure out what's the most frequent words that people use on Flickr. So we kind of combine some handcrafted rules and data-driven method to figure out a set of top keywords that encode common human activities on Flickr. For example, like building a house, party, church, graduation ceremony, outdoor activity, and etc. So here are the top 15 most frequent kind of stories. And now we collect a bunch of this Flickr album, and for each album, like we say, we ask 2 online crowd workers to pick 5 photos to form a photo sequence and write a story for that sequence. We ask 2 people to do that. So we collect 2 sequences, and each of the sequence have 1 story. And like I said, we want to collect more reference. So in the second stage, we show these 2 photo sequence to the other 3 crowd workers. And we say, hey, please pick 1 photo sequence you like and write a story for it. So at the end of the day, every photo album will have 2 image sequence and 5 story in total. So it is possible that some photo sequence is just harder to form a story. So it can be that all other 3 workers all pick the same photo sequence. It happened. But in total, we will have 5 different stories, okay? And for comparison, we actually collect a smaller set of image captions for isolated images in the photo sequence. And we also collect captions for the sequence of images. We call it DII, means a description for image in isolation. DIS means description for image in sequence. And the story itself, we call it SIS, is story for image in sequence. Okay. So this is the interface we use. You can see that, okay, you can navigate the entire photo in the same album. And you can, every time you click on them, and we'll create a card in the story, we call it storyboard. And you can write the story in the story card, in the photo card. And you can also swap the order if you want. And we also attach the whole story at the bottom of the storyboard so that you can see, you have a sense that it will be a coherent story rather than isolated captions. Okay. So what do the story look like? This is an example we pick on paper. So you can see from left hand to right, it's 5 photos. It's a story. And let me read this story quickly. A discus got stuck up on the roof. That's the first photo. Why not try getting it down with a soccer ball? That's the second photo. Of the soccer ball goes. That's third photo. It didn't work, so we try a volleyball. That's fourth photo. And now the discus, soccer ball, and volleyball are all stuck on the roof. That's the last photo. Right? That's a story. And if you compare them with the isolated image caption, it's very different, right? For example, left-hand side, the first photo is a black frisbee is sitting on the top of a roof. Second photo is a man playing soccer outside of a white house with a red door. And you can see that the caption tend to focus more on the visual details, the color, the shape, the position of the photo, which when you think about when you describe a photo to your friend, you don't really care that much about those visual details. You kind of describe in a way that encode the more social context so that people can understand it better. Okay, and at the end of the day, we did this data collection for 10,000 Flickr albums. That means at the end of the day, we collect basically 20,000 unique photo sequences, and we collect 50,000 unique short stories. And on average, we have some statistics about the data. On average, each album has around 20 photos, and it probably take 8 hours to finish each album. So did we get what we want, right? So we, at the end of the day, we did the analysis again, right, to see if at least the abstract terms is more frequent as we expected than the brown data set, which actually happened. Actually, all the collection, including all the captions we collected, have more abstract terms. They actually most of them is higher than 20%, and it's a lot more than brown data set. And we didn't have a good theory about why even the caption kind of increased their abstract terms. Probably because the sequence or the photo we kind of focus is mostly encode human activities, which is pretty different from, say, ImageNet. A lot of them are static objects or scenes. Probably that's why, but we didn't do further analysis about why. But I know that at least the data set we collected has more abstract terms. And the other thing we calculated is back then we have a 5-gram language model, which is trained on a lot of English data scraped from the internet. And we use that to calculate the perplexity. And for perplexity, the lower perplexity means the language is similar to the language you train your language model. And it turns out the story has the lowest perplexity as compared to captions and as compared to the brown data set, which means the language that we collected in the story is closer as compared to other data sets, closer to more modern or internet English. So now we know the format of the data set, right? It's the you have a input of a sequence of 5 photos, and it follows the order 1, 2, 3, 4, 5. And output is a short story describing that photo sequence. So how to actually generate stories in 2016, right? So back then we actually worked with the VQA people, so it's probably very straightforward to extend all the image captioning technologies. Basically, you have an encoder that can go through the whole sequence to encode a sequence of images, right? And back then we use a simple RNN. And you also need the decoder that goes through the encoded output is probably mostly a embedding vector. And you try to learn how to optimize for generation. You generate stories based on your encoded information. That's at a very high level, that's how we did generation. So this is the example output, right? The family got together for a cookout. They had a lot of delicious food. The dog was happy to be there. They had a great time on the beach. They even had a swim in the water. The last sentence is not entirely correct. I understand that, but even this took us some effort to figure out. So we actually tried different version of decoding tricks. And initially we think, okay, let's just do bin search, which is very straightforward for captioning and for probably for VQA. But it turned out we realized that doesn't work very well. So we shrink it, narrow down, lower the bin size. And at the end of the day, we just say, okay, let's try greedy. And it turned out the greedy works better than the bin search. We didn't really know why, but that's what happened. And we also try to add some penalty in the decoding time as a penalty to duplications. We also try to use the image caption output to basically adjust the weight of the word in decoding time so that the story generation model kind of need to agree with the caption model. If you say some words that the caption does not have it, you'll get a lot of penalty. So that's a decoding time trick. And it works better. It works better. And this is the initial paper that we introduced the task. And we kind of want to show that by adding a little bit trick, using your understanding toward what is a story, it can actually improve the output quality. So let's talk about the next step is obviously the evaluation, right? And how to evaluate things like this, how to evaluate the generated story. And first of all, evaluating NLG, natural language generation output is generally hard. It's still an open question, right? And evaluating story, in my opinion, is very hard. It's harder because it has more subjective component. It look at the larger and more diverse language space. And it's not even easy for humans. If I give you two stories, ask you to rate, sometimes people don't agree, right? And so we know it's harder for computers. It will definitely harder for computers because even humans have hard time to do that. So when we introduce a task, we kind of make the decision, like underlying subtle decision that we want to prioritize human evaluation. We know this is a task. The evaluation itself is a research question. It's an open research question. So we decide to stick with human evaluation a lot, and we respect human evaluation results. So in the initial paper, this is the question we use. We ask the human raters, if this were my photo, I would like using a story like this to share my experience with my friend. It's a statement. And we ask the human rater how much you agree with this statement. It's a 5-point Likert scale from strongly disagree to strongly agree. And we aggregate multiple raters score for each story. That's the initial human evaluation. And at 2 years, excuse me, 2 years after we published paper, we launched the first visual storytelling challenge. It's a shared task, co-locate with NACO at the storytelling workshop, and we invite people to submit their output and we evaluate them. So in this challenge, 4 different teams submitted their stories, and we use human evaluation to decide the winner. And in that evaluation, we ask more questions, each focus on one specific aspect of the story. This is the exact question we use. We ask focus, this story is focused. We ask the story structure and coherent. This story is coherent. We ask, would you like to share this story? and we ask, do you think this story sounds like it was written by a human, and how visually grounded the story is, and how detailed the story is. This is the different questions we use in the storytelling challenge, the visual storytelling challenge. So as a result, it's as a for benchmarking, we actually put one human written story into the rating and to see how much better or worse that machine generated story can be. And it turned out in the short term, in short, humans are still pretty good. Humans are still outperform all the models in all the aspects, right? It can be depressing, but remember, this is 2018. And back then, we kind of think this result is actually surprisingly good. It's better than we expected, because if you look at some aspect, for example, like coherent, the score is not actually that far. So it means in some case, machine can generate a reasonable story, which is even comparable to human written stories. And after human evaluation, we understand that people from time to time still need to use automatic evaluation for different purpose, right? To benchmark your own model, or to provide feedback when you train your model. We understand that. So in the paper, we said, okay, let's compare the human ratings with all these automatic values and how correlate they are. We calculate different types of correlation. It turns out Meteor is a lot better than Blue and Skip Salts. So in the paper, we suggest that, okay, if you really need to use automatic evaluation for reasons, Meteor is probably the one you want to use, which people did. However, very soon at 2018, and this paper came out, they tried to use different metrics to provide feedback in their training or learning process. It turned out it's hard to pick one, because many automatic evaluation tasks, it's probably like each component or each metrics capture one aspect or certain aspect of the generation output. It's just very hard to decide which one to use. And it's even more interesting that later in 2019, we did a strange thing. We used one of the model to generate a visual story, and we ask humans to edit that story. So we have a reasons to believe that the edited story is better, right? And when you use all this reference-based automatic evaluation, it's just getting worse. All these scores decreased. Probably for some people, this is obvious, because it's kind of shift the distribution away from the training data, which is true, but it also shows some limitation, right? In some use case, you should not just stick with this automatic evaluation, but this is the status of the thing. If you want to know more, this year, which is going to happen in less a week, if you are going to ACL, we have a paper saying that if you have been working on visual storytelling like us, and you have been collecting a lot of human rating data, either direct rating or ranking rating, you can actually try to learn a ranker for visual stories, right? That's what we want to say in this paper. A lot of details, a lot of interesting explorations. I encourage you to read the paper, or even better, if you happen to go to ACL, please talk to our students. So let's talk a little bit about the development of the generation visual storytelling technology. So before I start, I kind of want to say that the trying to focus on the figurative or evaluative language is not just us. It's not just us want to do this in vision and language data. Around probably similar period of time, there are a set of different efforts try to push the boundary of the descriptive language to more figurative language, right? For example, this is a paper try to figure out what is a humor in cartoon captions, right? Because if you look at the figure alone or the caption alone, you cannot figure out the joke. You need to put them together to figure out why it's funny, right? And that's one paper from Microsoft Research tried to do that. And this is a paper in 2018 and try to generate the puns in captions. For example, here, my favorite example is the bear kill the lion with its bare hands. Like bare hand is a pun. And when I see the paper, it was like, why? But to me, later when I think about it, it's actually an effort try to poke the wall of descriptive captions and try to add some creativity into it. And this one is a more famous work at the CVPR in 2019 and try to add a personality trait to captions. All right, so there are some effort try to add some flavor to your caption language. And that's back to our story, right? Like I said, in 2018, we launched the first visual storytelling challenge. And so far, that's the only one we did. That event actually encouraged a group of people that try to propose new technology or use new approaches to generate visual stories. And this is one example. This team actually get to the best human ratings in the challenge, but they submitted late, so they didn't get an award. But this is basically the highest performing model in the challenge. It's a team from Korea, and the idea is basically use a BioSTM to do the encoding, and you also use LSTM to do the decoding. This is also another famous one, and this is the aerial model from Santa Barbara. And the idea is that, like I just said, no metrics are perfect. So they take a more reinforcement learning kind of approach. You create an environment and you try to use that environment to give feedback to your generation model to figure out, use a more data-driven way to figure out what is a better or good story. And this is a paper from Carnegie Mellon in 2020. They explicitly compose different type of rewards in visual storytelling. For example, they combine how relevant the caption is to the image, how coherent the text is, how expressiveness the language is, and they combine all these factors in their reward function. And I would probably say this visual story, after this visual storytelling challenge, the stories actually became more fluent and coherent. I would imagine those are probably even more true today, given we have all this big language model. At least the fluent part will probably definitely be true. If you look at the results back in 2000, the shared task itself, the smallest gap happens in the written by human and coherent, these two particular aspects. And it is probably fair to say that story generation model, at least in visual storytelling task, it's kind of fairly good in being fluent and being coherent. That's probably true. Well, however, if you look at the story generated by the machine and you compare with the human written story, one thing you will notice is that machine generated stories are boring. It's definitely fine, it's fluent, and it's coherent, but it's kind of boring. It's still very far from human written stories, right? And so back then we were thinking, okay, why can we? Of course, I know there are many factors contribute to this situation, but can we narrow it down to a thing that we can improve, right? And the immediate response from our thinking is that, okay, one reason can be visual storytelling data set is relatively small. If you compare with other vision to language data set like Coco caption is basically a million captions, and VQA is also pretty big. even ROC story, which is not a vision to language data set, it's a story text, pure text story data set, is still basically double the size of visual storytelling data set. And visual storytelling data set only has 50,000 stories, which is probably very small in the world of vision to language data set. And the other reason, if you remember all the papers we talk about, right, they kind of have a sequential encoder that can encode the image sequences. However, they didn't try very hard to do anything to model or use the relations between the images or relations between the object, entities, items in different images, basically the inter-image relations. No one really tried very hard to do that. And understandably, it's probably also hard to do it, but just especially when your training data is this small, it will probably be useful to include some relations between images to help the generation. So what can we do? One, we should probably use external resource if your training data is relatively small. And two, you should try to connect at least neighbor images to improve, to help your story generation. So back in 2020, in Triple AI, we tried the thing. We call it KG story. KG means knowledge graph. And the key idea is that instead of doing everything end to end as all other people did, we went after a more old school modular pipeline, which is you generate words from images, and then you generate story from the words, right? And we try to explicitly connect two neighbor images. And finally, we use external knowledge graphs and data set to help the generation. So the pipeline is actually kind of straightforward. It's a bit old school. This is the input, is a photo sequence. And you try to extract a set of words or terms from each image. It doesn't, in concept, it doesn't really matter what you can use, whatever extractor you have. You can use face identification, you can use object identification, you can train the model to do it. There are a lot of things you can use, right? You have a lot of different image labeler or extractors, identifier you can use to extract words or text from the image. And second, you can try to use external knowledge graph to figure out the connections between the words you extracted. Let me say it again. In this particular example we are looking at, the left-hand side of word is graduate as a noun, and the right-hand side is diplomas as a noun. And in knowledge graph you use, you can probably find the relations between them, right? This is the concept. Once you have a set of words, you can use any database or any knowledge graph you have to figure out the relation between them in the common sense. You can go into use a concept net or any common sense kind of graph and try to figure out, does these two words or two entities or two objects have certain relations that we already know in our database or knowledge graph? That's a second step. And in this particular paper, we say, okay, if you found one, you can generate one extra sentence to describe that in your story. That's what we did. This, again, extraction, enrich, we call it enrich, but actually you are playing games with your knowledge graph. You just try to figure out the only words that has related or associated with each other in certain ways in your data. And you can do generation based on that information. Of course, there are some pros and cons, right? And this discussion is probably somewhat relevant to people's discussion to all the neurosymbolic systems. So for example, to me, the most interesting part is that by go after this modular approach, you kind of translate a kind of more difficult task into subtasks that you know a lot better. You kind of already know how to extract terms, labels, and words from images. There are a lot of things you can use. And you also have a lot of knowledge graphs. You already kind of know how to find the relations between two nodes on a graph. There are many algorithms can help you do that. And we also know once you find the paths, you know how to optimize or find the best one. We have a lot of work in this area. And finally, when you have a set of words and you try to do generation using that words, it's basically a text-to-text generation task. We already kind of know how to do it. So it basically breaks down a complicated, tricky task into smaller tasks that you know what to do, right? And technically, this doesn't only apply to vision to language tasks. You can do it with text-only story generation. And of course, the drawback of this approach is that, well, modular pipeline is probably arguably harder to work with. There are reasons why people want to do things end to end, because when you have a modular components, sometimes you need to figure out a way to that and work with each other, right? It's like, for example, if your extractor extracts something that doesn't exactly match in your knowledge graph, you need to do some conversion. And there are things like that. And also training is not always easy. There are ways to do it. It's just some more work. And also the classic example is the propagation of the error. If your extractor has some obvious errors, probably you won't be able to fix it in the later downstream applications. There are some drawbacks. So if you look at the output, right, our approach actually add one sentence to the story. In this particular example, the one sentence, that's why we picked this story. The one sentence the model decide to add to the story is, even the dog had a great time. It make a lot of sense, right? That's the benefit you get. It adds some flavor, adds some interesting sentence to the story. And based on the human evaluation, like I said, visual storytelling tasks really into human evaluation. And it's actually human-like our generated stories much better, slightly better. But to me, the most interesting part is not that it's better in the vague, hand-wavy sense. The interesting part to me is that if you think about the KG story, the middle layer output, the middleware output, is actually human comprehensible, right? The words are human comprehensible, the KG you use are comprehensible, and you can try to explain that to your users. Again, it's sometimes you need to figure out a way to do it because some KG doesn't written for human to directly read them, but it's mostly human comprehensible. And that means you can allow the users to do manipulation. That is a really interesting part to me, that you can have the users upload their images and you extract the words for them, and that then manipulate the words so that they can control the generated story. They can add a word they want, they can remove the word they don't like, they can manipulate the order of the words. And you can actually try to build a system like this. In 2019, we actually did that for an earlier version of our model, which is entirely probably based on LSTM. We submit a demo paper to the web conference. It's cool. And one thing we learned from this is that sometimes generation model doesn't work the way that user expected. It's a cool finding. And I think given the model capacity we have nowadays, we can even do even better than 2019. This is an interesting direction I'm really interested in. And final question is that, okay, now since you spend so much effort to build, to find the edge, to go through the knowledge graph, why not just add more edges? Why just stop at one? So in 2021, we actually did that. We did a more fancy and complicated version of this line of work. We actually try to create a whole graph, and instead of just learn one extra edge, you learn the whole path of the story. This is a kind of cool paper. If you're interested, you can go to take a look. So finally, I want to very quickly talk about the applications. So when you work on vision to language, right, the one question you got asked a lot is like, why? Like, what's the application? Even the people work on image captioning or VQA, they got asked that question. Okay, I can ask arbitrary question to images, why? And very commonly, the argument is related to accessibility purpose, which is probably true for many descriptive languages. But again, we are working on more figurative, evaluative language. It's probably, I feel, it's not as easy to just use the accessibility argument to justify the work, because sometimes it's just personal or subjective, and you need to figure out the right use case in accessibility application for it. But I want to say something about potential applications. So this is not from us. This is from Stephanie. And they figure out one interesting application is that when you can send a robot into an environment, and it can try to tell you a short summary of the environment based on the photos it take. Right? That's a very cool application. It was published in the storytelling workshop we hosted. And to me, a application that seems to be more straightforward is content creation. If you look into all the social media content, some of them, probably 5 to 10% of them, has multiple images. And they try to say something based on the photo sequence in some sense, right? So to me, this is like a more realistic and practical applications that we can see every day. And one challenge to me is, like I said, there's still a gap between machine generated story and human written story. I think if you see a friend who posts a machine generated story we see here on Twitter, Instagram, Facebook, you will probably think, okay, what's going on with that guy? Or maybe he is testing some bot, right? You won't think, oh, this is a cool story. So inevitably, what will happen is human editing. Mostly you generate a draft for them and they edit the story based on the machine generated story. So we actually did some exploration on top of this idea of, can we learn to edit machine generated stories? When you collect enough parallel data before and after editing, it's probably you can train a AP, like a post editing model that learn to edit your machine generated story. So a little bit context of APE tasks are often used in machine translation, and in the post editing, automated post editing task, you don't assume you have access to the generation model. So you treat the text generation model as a black box. We were challenged a lot back in 2019 when we tried to publish this paper. People ask us, why do you assume you don't have access to that? And why don't you just retrain the model when you have more or better data, right? And nowadays, people don't say that anymore, because nowadays people know the sometimes text generation model, like all the large language model, GPT-3, or the foundation model, those models, it's just not available to you. It's just extremely hard to it's extremely hard to retrain the model. It's sometimes even very hard to fine-tune the model. So it makes sense, because nowadays you don't assume you have access to those models. And what you can do, you can collect the machine generated text, have someone edit it, it's usually your user, and you learn the pre and post edited parallel data, and to to learn to edit your machine-generated text. So for this paper, we actually collect some data that we show machine-generated story, and we ask mechanical Turk workers, say, hey, can you edit this story, make it better, right? So we did some analysis on the human edit, and it turns out mostly people kind of increase the lexical diversity, and sometimes they add more words, add more diversity to the text. Sometimes they remove the duplications. And it turned out you can, even with a simple LSTM model, you can actually learn from the parallel data, and it can actually improve all the aspects of the machine-generated story, right? We actually do human evaluation, and it turns out people just like the post-edited story a lot more. It's still probably sometimes worse. It's still worse than human written story, but if you are thinking about some applications, what you can do is you can collect the human editing data and try to replicate editing on top of your generation model. So in this example, you can see the edit model actually go through all the duplications and try to remove the phrase, the bride and groom, from 4 times to 2 times. It's obviously an improvement there, right? So I would say it's probably more helpful when your generation model is not that good. Yeah, so it's probably more useful in the early stage of your product deployment. So today we talk about the birth of the visual storytelling task. We talk about some evolvement of the visual storytelling technology. And finally, we quickly go through some potential applications. So to wrap up, I want to go back to the initial paper, which written by our amazing co-authors. In the opening of the paper says this: beyond understanding simple objects and concrete scenes lies interpreting causal structure, making sense of visual input to tie the disparate moments together as they give rise to a cohesive narrative of event through time. The question is, are we there yet? There are a lot of data around us, a lot of text, a lot of narrative around us based on images, but are we there yet? I think this is an open question, and before I end, I want to do a plug. So if you happen to go to ACO in a week, we are hosting a workshop called Into Writing that studies the writing assistant, intelligent and interactive writing assistant. And we have a lot of cool speakers. In particular, we invited 2 professional creative writers who use language model in their work, and they are going to give a talk and answer some questions. So if you're interested in writing support or large language model or creative use of language model, please come to our workshop. Thanks for having me here. So I think it's time to open floor for any questions. Thank you very much.